Hello, my name is Cenk Gündoğan and I am a PhD student at the Hamburg University of Applied Sciences. Together with my colleagues Christian Amsüss, Thomas Schmidt and Matthias Wählisch, we worked on a feasibility study on reliably propagating firmware updates in constrained low-power networks following the SUIT model. The common IoT deployment consists of cloud services and gateways that are powerful and resource-abundant enough to perform protocol translations and other more complex tasks. IoT devices, servers, sensors, and actuators are constrained in memory and computational resources and generally have low energy budgets. The connectivity between cloud services and gateways is considered to be perpetual, while IoT devices experience disappearing links due to sleepy nodes or wireless interferences. We know from general-purpose devices and the Internet that software updates are necessary and part of the lifecycle management of any serious deployment. We are facing more and more IoT-related security threats, so increasing security demands require similar practices for the IoT. A secure and reliable firmware propagation in low-power regimes is therefore mandatory. However, the proper distribution of firmware updates is resource-consuming. Even for general-purpose deployments, they show as peak loads in the Internet. IoT networks mainly transmit sensor values of a few bytes, but firmware images are 1 to 2 orders of magnitude larger. Actually, several hundreds of kilobytes or a few megabytes are typical firmware sizes. The bandwidth limitation on constrained networks calls for new approaches, since delivery attempts of the firmware itself in large-scale deployments can lead to the denial of services and other security threats. The research question we followed in this paper was whether we can leverage the benefits of information-centric content replications to perform secure and reliable firmware rollouts at large scale for the constrained IoT. In the remainder of this talk, I will present the building blocks of our firmware rollout mechanism, then I will present our experimental evaluations, and I will then conclude with a summary and outlook. SUIT is a recent IETF working group, and they focus on defining a firmware update solution that is usable with Class 1 devices. This means devices with 10 KB of RAM and 100 KB of flash memory. In the big picture, vendors create firmware binaries and compile meta information into respective manifest files. These manifests are integrity protected and possibly encrypted. An operator distributes manifest and binaries into the infrastructure, and IoT deployments can then securely retrieve necessary updates. We define a naming scheme for manifests and binaries that promotes the aggregation of forwarding state. The first name component is a deployment identifier, followed by the vendor name and device class. The software version is a Unix timestamp, and the vendor defines update schedules for device classes separately. Devices then discover software updates following the predefined release cycles. The manifest file definition is based on the work of SUIT. A payload indicator points to the name of the binary. The payload digest is later used for integrity checks, and with the binary and chunk sizes, the IoT devices know how many chunks to request. The manifest itself is cryptographically signed with the vendor private key. The actual update process looks like this. An IoT device requests a specific manifest file version. If it exists, then the correct manifest is returned. If the manifest is valid, then the binary retrieval starts and chunks are requested until they assemble the full binary image. It is then verified against the payload digest in the signed manifest file. If everything is okay, then the firmware image is written to the correct flash region and the bootloader boots the new image. We look at two different retrieval strategies later in our evaluations. In the first strategy, multiple nodes on a path request firmware chunks concurrently. In the second strategy, nodes block downstream requests as long as a local binary retrieval is running. This results in a cascading binary propagation, where only a single node on a path is performing the update. The version discovery is jittered to not induce link stress in large-scale deployments. We use an indirect version discovery to reduce the number of version pollings. A forwarder inspects incoming version requests, and if the device class matches, then the local process ID of the update component is added to the pending interest table. Returning manifests are therefore forwarded downstream, but they are also locally delivered to the update process. The RAM is usually too small to hold the full binary. Chunks are therefore stored in persistent memory, and instead of using a separate NDN cache, we use the same buffer for serving cache hits. As an optimization, forwarders can locally deliver chunks from overlapping update processes. Alright, we now progress to the setup and results of our experimental evaluation. We performed all experiments in the IoT Lab testbed on real IoT hardware equipped with the IEEE 1504 transceivers. Our software platform uses IoT operating system Riot and the CCN Lite network stack. 30 devices and one gateway node form the illustrated multi-hub topology. In the evaluated scenario, all nodes start a single version discovery and retrieve a firmware update. The initial requests are jittered with a few seconds to prevent high link stress. We focus our evaluations on the path marked in red from the gateway to the node N7 because it has the highest hop count and will experience the highest traffic load. Each node is configured to perform 3 retransmissions on the link layer in milliseconds range, 3 retransmissions on the network layer with a 2-second interval, and infinite retransmissions on the application layer with 10-second interval. First, we assess the update progress over the experiment duration for the concurrent and the cascading retrieval strategies. We choose 4 different binary sizes, where the smallest image consists of 1,000 chunks and the largest image of 4,000 chunks. In the concurrent retrieval scenario, we observe a fast progression for nodes closer to the gateway, while nodes further downstream have much slower update progress. In the extreme case, it takes almost 30 minutes to complete the binary retrieval for devices farther away from the gateway. When binaries cascade step by step along the path, then we see a different progression. There are no overlapping retrievals anymore, and updates finish much quicker than before for single nodes. However, while it now takes around 5 minutes to deliver a binary, the overall rollout takes a little bit more longer. We learn from these observations that cascading deliveries yield relaxed network conditions, which can be beneficial for application-level cross-traffic. We now look at the chunk retrieval rate per second over the experiment duration for both retrieval strategies. With concurrent updates, we observe that retrieval rates are very low for downstream nodes. While there are a few instances that count around 60 chunks per second, the majority counts below 5 packets. For N7, which is the farthest node and therefore the extreme case, the average retrieval rate over the full experiment is 2 chunks per second. Again, the picture changes for the cascading setup, much more chunks complete per second. Especially for the extreme case, node N7, we observe an increase for the average retrieval rate that is almost 12-fold. Nodes request chunks iteratively in a stop-and-wait fashion. Packet loss leads to retransmissions in the seconds range, and this immensely degrades retrieval rates. Next, we have a closer look at these retransmissions. In this evaluation, we group chunks into blocks of 100 chunks and count chunk request retransmissions for each chunk block for the node with the highest hop count, N7. We distinguish between retransmissions that happen on the network layer by NDN and retransmissions that happen on the application layer after NDN was unable to recover a chunk. When chunk retrievals happen concurrently, then we observe on average 20 retransmissions per block. Interestingly, in many cases, NDN is not fully able to recover lost chunks, so that the application performs the much slower retransmissions for 1 to 5 times per block. The cascading delivery experiences overall much fewer recovery attempts and virtually no application-level retransmissions. Only the first chunk has an excessive number of retransmissions because the upstream node denies all requests while it completes its own process. We learn that concurrent deliveries greatly saturate available network resources. In our last assessment, we observe update completion times using two different scenarios. In the first setup, a common binary is delivered to all nodes. This is also the setup for all previous measurements. In the second setup, we use individual binaries for each device. This limits cache hits only to retransmissions, and chunks for each node need to traverse the full path at least once. With the concurrent strategy, the common binary rolls out to all devices in about 30 minutes, while the individual binaries complete in about 2.5 hours. The cascading setup shows similar results for both binary modes. We observe that individual binary retrievals degrade the network performance and heavily slows rollout times. We conclude our feasibility study with the following takeaways. First, an information-centric content replication fosters efficient and reliable chunk transfers. Second, concurrent and uncoordinated distributions result in high link stress. Third, a cascading delivery relaxes strain on network resources. And last, deployments with common binaries benefit from in-network caching, which speeds up rollout times. In our future work, we want to evaluate the distribution of partial firmware updates and explore enhanced security measures to ease voluminous data transfers. Thank you for listening. We support the recent ACM initiative on reproducibility. You can find our code and documentation at this GitHub URL.